about the motion of charge particle and the path traveled by them in a uniform electric field. Okay, so you write motion of charge particle, motion of charge particle on a uniform electric field. Motion of charge particle in a uniform electric field. Okay, you see any charge whether at rest or in motion, any charge whether at rest or in motion in a uniform electric field will experience an electric force F is equivalent to QE. Okay, any charge whether at rest or in motion in a uniform electric field will experience an electric force F equal to Q. Suppose this is your uniform electric field, one charge is here. So you see the force acting on the charge is along this direction, that is QE. If it is positive, then the force will be along the direction of electric field, and if it is negative, then the force will act opposite to it. Do you follow me or not? You see, if the electric field is like this along this direction, this side must be positive and this side must be negative. You may put two plates, one is positively charged and another is negatively charged. So electric field or field lines will be directed from positive to negative. So this is suppose uniform electric field. In uniform electric field, two charges are there, one is your positive and another is your negative. Suppose at rest, the force acting on positive charge is QE along the direction of electric field, and minus QE, okay, or you say QE on the negative charge opposite to electric field. Okay, if the charge particle will experience force, then it must be accelerated. Then acceleration of the charge particle will be what? A is equivalent to QE by N, and which is constant. You see, this acceleration is constant because you see E is uniform, charge is constant, mass is constant. So overall the acceleration of the charge particle will be constant. Clear? So since the charge particle experiences a constant accelerations, so all the kinematic equations V equal to U plus at, S equal to ut plus at square, V square equal to V square plus 2S, all are applicable to this motion of charge particle also. Okay, suppose a charge particle, is released at rest. Suppose a charged particle is released at rest. That is U equal to 0. Initial velocity is 0 in a uniform electric field. In a uniform electric field as shown in figure. Suppose it is released at rest, U equal to 0. Then you see it is accelerated along this direction with the value what? QE by m. Then it will acquire velocity during in the course of motion. It will gain velocity, kinetic energy, and it is displaced from one point to another. Not that. A charged particle is released at rest in a uniform electric field. Then, if a charged particle, then velocity acquired by it in time t will be what? You see, V is U plus at, but U is 0. Charged particle is released at rest, so U equal to 0, so V equal to T. A is how much? QE by M into T. So this is the velocity acquired by the charged particle in a uniform electric field in a time T. Clear? So what will be the kinetic energy acquired by it? Kinetic energy acquired by it will be what? Half mv square. Not that. Half mv square. You put the value of v here, so it will be what? Half mv square. That is m by 2. V square is q square e square t square by what? M square. Not that. Half mv square. Q square e square t square by m square. So what we are getting is q square e square t square by 2m. Clear? This is the kinetic energy acquired by the charged particle in a uniform electric field in time t. Clear? Then distance or displacement covered by the charged particle in time t. Distance or what? Distance or displacement covered. Distance covered in a time t will be what? Will be s equal to ut plus half a t square. So u is 0, half a t square. Half a is how much? QE by m into t square. Half QE by m into t square. So it will be what? QE t square by 2s m. So this is the velocity acquired, this is the kinetic energy acquired, this is the what? Your distance or displacement covered in time t by the charged particle in a uniform electric field having acceleration equal to QE by m. Okay? Then you see, if the charged particle is not released at rest, if it has some initial velocity, then what will happen? here V equal to U plus AT, that is U plus QE by M into T. And here is also UT plus QET square by 2M. Okay. You see, for the motion of the charged particle, you see, for the motion of the charged particle, the work is done by the electric field here. We are not doing work. For the motion of the charged particle is accelerated, gained velocity, gained kinetic energy. This is because of electrostatic force or electric field. So in this case, electric field itself does work, not that, on the charged particle. Suppose V, capital V, be the potential difference across the two plates. Okay. So electrostatic work done, on the charged particle will be W equal to QV. This V is not velocity. This V is accelerating potential. You see, you must have read in gravitation chapter, gravitational potential. Gravitational potential work done in bringing a unit mass from infinite to that point. Gravitational potential is work done in bringing a unit mass from infinite to a point. Similarly here, electric potential is defined as work done in bringing a charge from infinite to that point. I will discuss electric potential in next class. Okay? So, for the time being, you remember, in comparison to gravitation, you see here W equal to mv, m into potential difference, here q into potential difference. Because of potential difference, charge is moving. Not that. So, work done is qv. But work done equal to what? Change in kinetic energy. Initially, charge particle is released at rest. Finally, it acquired kinetic energy half mv square. So, according to work energy theorem, work done is change in kinetic energy. Okay. So, but this is an expression for velocity acquired by the charged particle in terms of what? Accelerating potential. This is important formula also. This is the expression for velocity acquired by the charged particle in a uniform electric field in terms of accelerating potential. This potential will be clear later on. Okay. So, is then if the charged particle is in equilibrium, if the charged particle is in equilibrium, if the charged particle is in equilibrium, that is net force on it is 0. Okay, F net is 0. The charged particle either will be at rest or it will move with what? Constant velocity. Not that. So you consider, you see, you consider a vertical electric field. Suppose this plate is positive charge and this plate is negative charge. So electric field is vertically directed. Uniform electric field, say, suppose it is a charged liquid drop. It is suppose negatively charged. Okay. So on this charge, force will be what? QE opposite to electric field. Not that. since it is negative charge, and its weight is directed vertically down. Not that. Okay. So you see, since the charge particle is in equilibrium, then what we can write? QE equal to mg. QE equal to mg. Or charge on the charge particle is mg by E. Again, from quantization of charge, you know Q equal to Ne plus or minus Ne is equivalent to mg by E. So you can also found out number of electrons on the charge particle. Number of electrons gained or lost by the charged body here. So N equal to what? Mg by E. Okay. Okay. Then we will describe path followed by the charge particle in a uniform electric field. Path followed by the charge particle in a uniform electric field. Okay. Path followed by the charge particle. Path followed by the what? Charge particle. Suppose this is a uniform electric field. Okay. Suppose you are projecting a charge particle along this direction with initial velocity. It is accelerated along this direction. That is, it will experience some force along this direction. So it will accelerate and will follow straight line path. Will follow what? Straight line path. Okay. Will follow straight line path. You see, you may project along this direction also. Suppose you are projecting a negative charge along this direction with velocity. You see, it will accelerate along this direction because force acting on it is opposite to electric field. If a positive charge is projected on the direction of electric field, it will follow the straight field lines, and path described by it is linear, straight line. And if a negative charge is projected opposite to electric field, it will experience force along opposite to electric field, that is along same direction of projecting velocity. So the path followed will be also what? Straight line or linear for theta equal to 0 degree and 180 degree. Okay. For theta is 0 degree and 180. That means theta means velocity and electric field. Direction angle between projecting velocity and electric field. The charge particle either enters into electric field parallelly or anti-parallelly. The path followed will be straight line. Then what about if the charge particle will enter to the electric field at any angle besides 0 and 180, 60, 30, 40, 120, 90? Okay. In this case, path is straight line or linear. What about the path followed by the charge particle? If the charge particle enters into a uniform electric field at any angle besides 0 degree and 180 degree. Okay? We will discuss these things. You see, it is very simple. You see, suppose this is the representation of uniform electric field. Say, you see, if a charge particle is projected like this, you see, then what can you see? A force QE always directed vertically downward, so its path will be like this. So it is parabolic. Okay, path followed by the charge particle is parabolic. Okay, we will So the path followed by a charge particle is parabolic, and we will derive the equation of trajectory just like your projectile motion. It will satisfy the equation of parabola. But here we will take simple example. Suppose charge particle is entered into uniform electric field at 90 to electric field. Okay. For simplicity, take a charge particle which is entered into a uniform electric field normally, or at right angles to uniform electric field. Suppose you see this is the uniform electric field conditions. Okay. This is the uniform electric field representations E. Suppose the charge particle is projected with an initial velocity u, positive charge, with an initial velocity u along x-axis. We take this as positive y-axis. Okay. And this is positive x-axis. So the charge particle is projected at right angles to uniform electric field with initial velocity u along x-axis. Immediate, as soon as the charge particle is entered to uniform electric field, a force acts upon it along y directions. Not that. So path cannot be linear. So it will automatically what? Parabolic. Okay. So you see force is along y direction. You see Fy, that is AYE, not that, AYE or AE. Okay. Along the direction, y direction force is there. So acceleration is also there. You will what? QE by m into AY force. So okay, force acting on the charge particle along y direction is Fy equal to MAY. Okay, and Fy is what? Q into Ey, or simply, so what is your acceleration? Ay is what? Qe by m. Initial velocity along x direction is u. Initial velocity along y direction is 0. Right? Because the charge particle is projected horizontally. Charge particle is projected horizontally. So initial velocity is what? Complete velocity is along x direction, which is constant from the motion. In the concept for projectile motion, one component remains constant, another component is variable. Here you neglect the gravitational force. Since the gravitational force is the weakest one, so in comparison to electric force, you neglect gravitational force here. Okay. Let after time t, the projectile is here. Okay. And this is x, and this is what? Y. After time t, suppose the projectile is here. So its position is x and y. Not there. Along y direction, it has covered displacement y. Along x direction, it is x. Not there. Then how can you find out x? X is what? Uxt plus half axt square. Ax is 0 because ux is constant. So there is no acceleration along x-axis. There is the acceleration along y-axis. So it is uxt, that is ut is x, and what will be your t? X by u. Okay. Again you see, taking motion along what? Taking motion along y direction. Taking motion along y direction. But you can write y equal to uyt plus what? Half ay t square. But uy is 0 because the charge particle is projected horizontally. There is no initial vertical component of velocity. So what you are getting, y equal to half ay is what? QE by m acceleration on the charge particle along y axis. What is t? You put the value of t, taking on this x by u 1 square, x by u square. So what you are getting, you see QE by 2m u square into x square. You see this is the equation relating the instantaneous position y and x for a charge particle, which is in the form of, you see, in mathematically it is in the form of y equal to ax square. So which is equation of parabola. This equation is in the form of mathematical relation y equal to x square. So which is equation of what? Parabola. Which is equation of parabola. Okay? Which is equation of parabola. Do you follow me or not? You see, this is all about the motion of charge particle in a uniform electric field. You see, from these explanations, we have concluded that if a charge particle enters either parallelly or antiparallelly to a uniform electric field, it will describe a linear path. Okay. And besides this, if the charge particle enters to electric field at any angle besides 0 and 90, 0 and 180, it will describe parallel always. For simplicity, we are taking just like your horizontal projectile. Charge particle enters into electric field at 90 degree. Okay. Right, torque acting, it is a 3 marks questions. Torque acting on an electric dipole, torque acting on an electric dipole in a uniform electric field. It is there at potential of electric potential. Torque acting on an electric dipole in a uniform electric field. You see, consider an electric dipole. Consider an electric dipole consisting of 2 charges plus q and minus q, and length 2l. Consider an electric dipole of length 2l consisting of 2 charges plus q and minus q, having dipole moment p, that is p vector is equivalent to either charge into separation between 2 charges. Okay? You see. Suppose angle between dipole moment vector and electric field vector is what? Theta. That means consider an electric dipole of dipole moment P, length 12, making an angle theta with external electric field E. Then you see, since it is a positive charge, force acting on it is QE along the direction of electric field, and the force acting on negative charge is minus QE opposite to electric field. Not that. Then you tell me what is the net force on the dipole? What is the net force on the dipole? Is 0. Always. Any dipole in any orientation, if it is placed in a uniform electric field, the net force on it will be what? 0. QE plus minus QE equal to 0. You see, the charge net force on the dipole is 0. But you see, these two forces are equal and opposite, but acting at two different lines of action. They are not along the same direction, same line of action. You see, this force is along this line of action. This force is along this line of action. So these two forces are not along the same line of action. So they never cancel with each other. Not that. Net forces are 0. You see, net force is 0. Since two forces are equal and opposite and acting at two different line of action, no doubt net force is 0, but there is the tendency of rotation of the dipole in the electric field. Since the two forces are equal and opposite and acting at two different line of action, they constitute a couple or torque which tends to rotate the dipole so as to make it parallel with the electric field. This will create a torque, this will also create a torque, this force, then it will turn the dipole to make it parallel with the electric field. I will discuss why the torque tends to make it parallel with electric field, because at that position the potential energy minimum and system is stable. Later on I will discuss. Okay, but here two forces are equal and opposite and have a different line of action, so they constitute a couple or torque which is a tendency to rotate the dipole to make it parallel with the electric field. You see, this is the perpendicular distance between two forces. This is the, you see, this is the perpendicular distance between two forces. Then what is its expression? You see, if it is theta, this is also with theta, this is also theta, all the lines are parallel. So you see, sin theta is this by 12. So it will be what? 12 sin theta. Sin theta is this by 12. So this one will be 12 sin theta. So perpendicular distance between two forces is 12 sin theta. So what is the torque? Tau is equivalent to what? Either force into what? Perpendicular distance. Either force into what? Perpendicular distance. It is quite obvious. Torque expression for torque is either force into perpendicular distance between two forces. So either force is QE, perpendicular distance is what? 12 sin theta. So you see, QE into 12 into E sin theta. Okay, so it is what? Q into 12 is P, so P sin theta. It is the expression for torque acting on a electric dipole placed in a uniform electric field. This is in magnitude form. What will be its expression in vector form? P cross E. This is the expression for torque in vector form, P cross E. Clear? Then when the torque will be maximum, under what condition torque will be maximum? You see, tau max, if theta is 90. So tau max is P if theta is 90 degree. Got that? And what is the tau minimum? Is 0. Tau minimum is 0 if theta is 0 degree or 180 degree. Okay? So P sin 180 is 0, P sin 90 is maximum. Do you follow me or not? In next class we will discuss about electric potential, and in that chapter we will discuss what done on an electric dipole in a uniform electric field, potential energy of an electric dipole in a uniform electric field, which will be linked with the expression of what? Torque on the dipole. Clear?